Welcome back to PV Online. This video is going to deal with friction, and friction is something that we encounter all the time, and thank goodness that we do. If we didn't have friction, there would be no way for us to walk from one point to the other. Just imagine trying to walk on a slippery sheet of ice, how difficult that is. So friction is a force that opposes motion or impending motion. Now you're going to see these two words show up every once in a while, kinetic and static friction. And basically what happens is the kinetic friction is anytime you're moving, and the static friction is when you're stationary. The interesting thing is that the static friction is always larger than the kinetic friction. And that's why if you've ever tried pulling something or someone in a wagon, the hardest part is just getting it started. And that's because friction is actually larger than when you start moving. Friction depends on two things. Friction depends on mu. Mu stands for the coefficient of friction, and basically it's how rough the surfaces are. So if you have sandpaper, that's going to have a very large mu. If you have ice, it's going to have a small mu. And the other thing that it depends on is the normal. And that's why heavier objects, where the ground pushes up on it with more force, is going to have a larger frictional force than a lightweight object. So we have these two variables, the coefficient of friction and the normal. The coefficient of friction, sometimes you'll see this. Most of the time you won't, but if you do, just don't worry about it. It's treated the same. And the S would just simply be the static, and the K would be kinetic. Now, the one thing that's important about the coefficient of friction is there's no unit associated with it. It's simply a ratio of forces. It's a ratio of the frictional force divided by the normal force, so there will be no unit. The other just little side note, the coefficient of static friction is always larger than the coefficient of kinetic friction. All right, so we have this equation that we're going to be using for the rest of the unit. Friction equals the mu times the normal. So let's take a look at an example problem. This object the block is moving to the right, and it's accelerating to the right at 1.5 meters per second squared. So the acceleration is 1.5 meters per second squared, and it's directed to the right. And that's going to be important because that's going to dictate which force we're going to make positive and which force we're going to make negative. Now in this case, we have four forces acting on it: an applied force, we have the normal force, we've got the weight of the object, which is mg, and we've got the frictional force. And the little subscript k simply means that that's going to be moving. So the question is, it says determine the applied force required to accelerate this 5-kilogram block. So as we always do, we're going to start with Newton's second law. The sum of the forces equals mass times acceleration. I'm interested in the applied force, so at first, let's take a look at these two forces. These two forces are parallel with the acceleration, so those are going to be the ones of interest to us. Now, they're going in opposite directions, so I'm going to have to choose which one to make positive and which one to make negative. Get in the habit of making the force that's in the same direction as the acceleration is positive. That means friction is going to oppose it. So I have the applied force minus the frictional force is going to equal the mass times acceleration. So in order for us to find the frictional force, it is simply the mu times the normal. So now we've got to find out how much the normal is, and you need to realize that this block is not accelerating up or down. As a matter of fact, it's pretty static vertically. So these two forces have to be equal and opposite. They're balanced, meaning that the normal is going to equal mg. Now, since that's the case, I could come over here and say, you know what, the applied force minus friction, which is mu, times the normal, which is mg, equals the mass times the acceleration. The applied force minus mu has a value of 0.25. Do you see how there's no unit associated with the coefficient of friction? The mass is 5, g is 9.8. That's going to equal the mass times the acceleration, and the acceleration is 1.5. And now I can solve for the applied force. And so we get 19.8 newtons. Now, if I had just multiplied 5 times 1.5, that would have been 7.5. Why do you think that we needed so much more than 7.5 using just F equals ma? And that's because in addition to getting the block to accelerate, I also had to overcome friction. Whenever you're doing friction problems, the normal is going to be a big part of it. And so I want to go through real quick the different types of normals you might encounter. And let's just take a block that's on a surface, and it could be accelerating left or right, it doesn't matter. But in that case, I'm going to have mg acting down, I'm going to have the normal acting up, and let's say I have an applied force like so, and I have friction. That means my normal is going to equal mg. And as soon as you get to the point where you can just glance at the problem and go, okay, normal equals mg, it'll make these a lot easier. The second most common type of problem that we're going to get is a block on an incline. And when you have a block on an incline, this time I'm going to have mg acting straight down. I'm going to have the normal acting perpendicular to the surface. So do you see how this is actually up and to the left? And I'm going to have friction going to oppose the motion. So friction is going to act straight up the incline like so. And let's say that this angle is 30 degrees. So this angle is 30 degrees. And we know that this block is going to accelerate down the incline. Well, if your force is parallel, as friction is, with the acceleration, or perpendicular, as the normal is, those two are fine. The problem is going to be mg. mg, we have to break into components. We have to find out how much of mg is going into the incline, how much of it is going down the incline. Now what happens is I just made a right triangle by breaking up mg into these two components. I'm going to call this one the vertical component and the one going down the incline the horizontal component. Well, this triangle happens to be a similar triangle as the incline itself. And what's going to happen is that angle right there is going to be 30 degrees every time. So since this is going to be 30 degrees, my adjacent side is going to be mg cosine of theta. So part of gravity is going to be pushing that block into the incline, but it's also going to be pulling it down the incline. And the component of the gravity going down the incline is going to be mg sine of theta. The bigger the incline, the faster you're going to accelerate down because more of gravity is pulling you down the incline. The flatter the surface, the smaller the angle, you're going to accelerate less because more of gravity, more of your weight is going to get pushed into the incline. So now when we're focusing on the normal, instead of looking vertically just straight up and down like so, now I have to look at what's going on at this angle right here. And my block is not going to be accelerating off that incline, so I know that the sum of the forces are going to be equal 0 along this perpendicular component, which means these two forces are going to be balanced. So whenever you have an incline, your normal is going to equal mg cosine of theta. And the third, let's do our third and final normal that you're ever going to encounter. And that's going to be when you get something that looks like this. Suppose this time I have a block or a crate or a sled or whatever, but I'm now going to be pulling it with a force at an angle. So let's call this theta. And let's say that this force is causing the crate to accelerate to the right. While I'm doing my force diagrams, I'm going to have mg acting down. I have the normal acting up. And if I have friction, friction is going to oppose it, so I would have friction going to the left. So now if you look at this, remember, if the forces are at right angles, they're fine. They're fine. They have no influence on one another. We don't worry about them. Which one of those forces is going to be the problem child? Which one's going to be the one that we have to deal with? And you can see it's this applied force because it's at an angle. Well, it's no big deal because all we have to do is break that force into its horizontal and vertical components. And so in this case, I'm going to have F cosine of theta, and my vertical component is going to be F sine of theta. Now remember, when we're doing this, we're focusing on the normal. So I want you to just isolate what forces are acting parallel with the normal. And we know we've got the normal acting in the y direction. We have mg acting in the y direction. But we also have that guy, F sine of theta. So now when I come over here and I say the sum of the forces acting in the y direction equals 0, because I know they're balanced, this crate isn't going vertical. So the sum of the forces in the y direction equals 0. I have that the normal, I'm going to make anything going up as positive, minus mg, but I can't forget this guy, and he's directed up, so that's going to make him plus F sine of theta. Those all sum up to equal 0. That means my normal is going to equal mg minus F sine of theta. Now you know this from just your life experience. If you're moving a big couch or something like that, you pull up and at an angle. And the reason you're doing that is you're reducing the normal force, making friction smaller. All right, we've had a little introduction to friction. We'll see you next time.